Hello students, welcome to the course of Linear Algebra. My name is Dr. Girish K from Linear College Sangli. This course is for MSc1 Mathematics students of Shivaji University Kolhapur. Recommended books for this course are Topics in Algebra by Ivan Hustin, Linear Algebra by Hakman Kenneth and Kunj R. There are some books that are useful for the course are Linear Algebra, an introductory approach by Charles W. Curtis, and Linear Algebra, a geometric approach by S. Kumresan. These books are also useful for this course. All of you have already studied linear algebra at your graduation level. Linear algebra is actually study of vector spaces, linear transformation, and matrices. This branch of mathematics has grown from careful study of solution of system of equations. Since this is our first lecture, here in this lecture, we are going to define a vector space, and before beginning of a definition, we try to understand the behavior of solution of system of linear equation and differential equation. We know that if we have a system of linear equations with n unknowns, then one of the solution of system of equation may be something like x is equal to alpha 1, alpha 2, and so on, alpha n, and suppose another one is y is equal to beta 1, beta 2, and so on, beta n, then if we look at this n tuple alpha 1 plus beta 1, alpha 2 plus beta 2, and so on, alpha n plus beta n is also one of the solution of the same system. Similarly, also if lambda is a scalar or say real number or a constant, then lambda into alpha 1, lambda into alpha 2, and so on, lambda into alpha n is also one of the solution of system of equation. Similarly, if we consider the differential equation, and if we have f1 as one of the solution of a differential equation and f2 is another solution of a differential equation, then f1 plus f2 is also a solution of the same differential equation. And similarly, if we have some number and some constant, then lambda into f1 is also solution of given system, We consider solution of system of linear equation and solution of differential equation. There is some common factors in these two. If we look at the solution of system of equation, then the addition of these two will be again the solution of the vector space, and the scalar if you multiply by some number, then that is also solution of the system. And similarly here we have the same case. So this common behavior leads us to the definition of a vector space. Now we consider definition of a vector space. Now we define a vector space. Let capital F be an arbitrary field. Then the non-empty set V together with composition, addition, and scalar multiplication is called as a vector space if it satisfies following conditions. To define this vector space, we required addition of a vector. So it is a composition from v by v to v, okay, and scalar multiplication is from f by v to v. If these two are the composition on this non-empty set v with following condition, and the first one is this ordered pair v plus must be abelian group with respect to this addition. Second one is distribution of the scalar multiplication over the addition, that is alpha into u plus v is equal to alpha into u plus alpha into v. So this is the second property. Then third one is alpha plus beta into u is equal to alpha into u plus beta into v. This is the third property. And then we have fourth property is alpha into beta v is equal to alpha beta into v. The last property that must satisfied by this set is 1 into v is equal to v for 1 belongs to F. Now we consider some examples of vector spaces. Let C be set of all complex number, and we know that it is a field, and R means set of all real number is also field. Then C over R is a vector space. Note that here R is a field of the corresponding vector space. Here addition of two vectors is z1 plus z2 is equal to, suppose z1 is a plus ib and z2 is equal to c plus id, then their addition will be add real part into real part and imaginary part into imaginary part. So it is a plus c plus I into b plus d. So this is the addition. And if we have real number alpha, then scalar multiplication is alpha into z1 is alpha into a plus ib is equal to alpha into a plus I into alpha into v. So this is the scalar multiplication in C over R. Then since we know that C and R both are fields, it is quite easy to verify that C over R is a vector space. Now we consider another example, that is the space Rn, okay, which is contains an ordered n tuples. For example, x is equal to alpha 1, alpha 2 and so on alpha n, where these alpha i's are in capital R. Then addition of two vectors in Rn is, for example, x plus y is equal to alpha 1, alpha 2 and so on alpha n, the first n tuple that is x in Rn, and another is suppose y, which is beta 1, beta 2 and so on beta n. Then their addition is, we just add component wise elements. So that is alpha 1 plus beta 1, the second one is alpha 2 plus beta 2 and so on, last one is alpha n plus beta n. So this is the addition in Rn. And the scalar multiplication is, suppose lambda is a real number, then lambda into x is lambda into the number vector alpha 1, alpha 2 and so on alpha n, and the scalar multiplication is defined as lambda into alpha 1, lambda into alpha 2 and so on lambda into alpha n. Again, with respect to the two operations, that is addition and scalar multiplication, one may easily prove that this Rn is also a vector space. Now we consider another example of vector space. Let capital V be set of all polynomials over f of degree n. That is, p of x is equal to a naught plus a1 into x plus and so on, an into x raised to n, where these ai's are in capital F. Then V over F is a vector space with respect to addition defined as p of x plus q of x. We have two polynomials, then their addition is a naught plus a1x plus and so on, an x raised to n. Suppose this is a polynomial p of x, and another polynomial is suppose b naught plus b1 into x plus and so on, bn into x raised to n. Then their addition is defined as a naught plus b naught, then plus a1 plus b1 into x plus and so on, an plus bn into x raised to n. So this is the definition of addition. And similarly, if we have some scalar alpha in the field f and we have polynomial p of x, then their multiplication is defined as alpha into a naught plus alpha into a1 into x plus and so on, alpha into an into x raised to n. Now with respect to these two operations, this set V over F is a vector space. Also note that if capital F is a field, then F over F is also a vector space. Okay? And it is quite easy to show that this is a vector space because we know that F is a field, and by using all the properties of field, it is easy to show that F over F is a field. Here we consider the same addition that is in the field F, and the multiplication is also taken here as a scalar multiplication. So it is quite easy to prove that this is a vector space. Also, if we have a field F which is subfield of field K, then K over F is also vector space, okay, where addition and scalar multiplication is actually addition in a field K, and the routine multiplication of elements in K is taken as a multiplication, a scalar multiplication, and here scalars are taken from field F. So these are some examples of vector spaces. Now we define subspace of a vector space. Let V over F be a vector space and W be subset of V. Then this W is said to be a subspace of a vector space V if W itself is a vector space with respect to same addition and scalar multiplication that is in V. In that case, we say that W is a subspace of V. Also, we know that W is a subspace of V if and only if alpha into V plus beta into U belongs to W for all alpha beta belongs to the field F and UV belongs to capital W. Now we consider one example of subspace. Let R2 over R be a vector space, then we define W1 as the set of all elements of this type, that is ordered pair A0 where A belongs to R. Obviously this is subset of R2, and W2 is equal to ordered pair 0B where B is in R, then these two are actually subspaces of R2. Also note that W1 intersection with W2 is equal to singleton set 0, 0, which is a subspace of R2. But W1 union with W2 is not a subspace of R2. Not a subspace of R2. Dear students, in the first lecture, we have seen the definition of vector space and its subspaces with few examples. In the next lecture, we are going to see definition of homomorphism from one vector space to another vector space, internal direct sum, external direct sum, and linear span with some examples. Thank you.